In May 2021, New Jersey Mining Company announced the discovery of two gold-bearing quartz vein systems on private property in the Murray Gold Belt of northern Idaho. The main Badger vein turned up during routine road construction. Follow-up work uncovered a second quartz vein, roughly 30 centimeters wide, sitting beneath shallow gold-bearing terrace gravel. Samples from the Badger veins returned anomalous gold values, with the highest result reaching 18 grams of gold per ton. About 600 meters away, the company identified a separate system called the Argus vein. By the time of the announcement, the Argus system had been traced for around 130 meters through 8 trenches. Its quartz veins ranged from 10 to 50 centimeters wide, and some samples returned several grams of gold per ton. These results confirmed that the exposed veins contained gold, though additional mapping, trenching, drilling, and representative sampling were still needed to determine whether the mineralization continued at depth or carried any economic weight.
The Badger case illustrates something worth understanding before heading into the field. Erosion, road construction, excavation, and landslides can expose rock that was buried under soil or gravel for a very long time. A new exposure creates an opportunity to examine material that could not be seen before, but the exposure alone proves nothing about what lies below it. The Murray Gold Belt has a long mining history, going back to the 19th century, yet parts of the district received limited systematic exploration because of fragmented land ownership, restricted access, vegetation, and shallow surface cover. Some of those veins were already there when the old miners worked the area, they just went unnoticed. The Badger discovery did not happen because someone spotted white quartz and called it a mine. It happened because of the vein's geologic setting, its orientation relative to known structures, systematic sampling across the full width of the exposed rock, and laboratory assays that measured the actual gold content. Quartz is common nearly everywhere in the Earth's crust, and most quartz veins carry no economically meaningful gold. Gold turns up in several types of deposits. It can sit in river gravels, spread through large volumes of rock, bond with sulfide minerals, or concentrate inside hydrothermal veins. The veins are where this video stays. Deep in the crust, hot fluids circulate through rock and carry very small concentrations of gold and other dissolved elements. Those fluids may come from metamorphic reactions, magmatic systems, or other deep geologic processes depending on the deposit type. Fractures in permeable rock give them a path to move through. As temperature, pressure, fluid chemistry, and the surrounding rock all shift, dissolved minerals begin to precipitate. Quartz, carbonate minerals, sulfides, and gold fill open spaces or replace parts of the host rock. This process typically runs through repeated episodes, which is why veins often show banded, brecciated, or cross-cutting textures rather than a uniform fill. A fracture is any break in rock. A fault is a fracture or zone of fractures where the blocks on either side have moved relative to each other. A joint is a fracture with little or no visible displacement. A shear zone is a broader area of deformation produced by movement through the rock mass. These are related but not interchangeable, and the distinction matters when reading geologic maps or old mine reports. Faults and shear zones can matter in gold exploration because they may channel hydrothermal fluids over long distances. That does not make every fault worth investigating. Many are completely barren, and many mineralized structures carry only low concentrations of valuable metal. The full geologic setting has to be read, not just the presence of a crack. Quartz appears in veins so often because silica is common in hydrothermal fluids and precipitates readily as conditions change. A white quartz vein cutting through darker host rock can be easy to spot from a distance, but quartz alone says nothing about gold. More useful observations include the vein's relationship to known structures, signs of hydrothermal alteration in the surrounding wall rock, sulfide minerals, repeated vein sets, brachiation, and geochemical results from the lab. Research published in 2024 proposed a mechanism that may help explain how large gold accumulations grow inside some orogenic quartz veins. Quartz is piezoelectric, meaning mechanical stress generates an electrical potential within the crystal. In laboratory experiments, researchers placed quartz in a gold-bearing solution and applied repeated stress. The stressed quartz produced enough electrical potential to deposit microscopic gold particles from the solution onto the crystal's surface, and gold accumulated preferentially around existing gold because gold conducts electricity. This provides a plausible explanation for nugget growth in certain earthquake-related quartz veins. It does not mean that every earthquake produces gold, that every fault contains gold, or that piezoelectricity drives every gold deposit on the planet. Hydrothermal fluids have to already carry gold, and the structural, chemical, and physical conditions have to line up. This is one possible concentration mechanism inside a much larger and more complicated ore-forming system. The age or appearance of a crack cannot be reliably read from color alone. A clean fracture can look recent but result from erosion, stress release, frost action, blasting, or a landslide. A mineral-filled fracture records fluid movement and precipitation, but it may still carry no gold. The question worth asking is not whether a crack looks old or fresh. The question is whether the structure shows evidence of hydrothermal mineralization and whether representative samples contain measurable gold. A vein contains minerals deposited inside a fracture or replacing rock along it. Quartz veins commonly appear as white, gray, translucent, or glassy bands cutting across the host rock. Some run straight and continuous. Others form irregular networks, parallel sheets, brecciated zones, or dense networks of narrow veinlets called stockworks. Recognizing the difference between a mineral-filled vein and an ordinary break in the rock is the first practical skill worth building. Fresh road cuts, stream banks, excavations, and landslide scars can expose bedrock that has not seen air in a long time, but access and sampling must be legal and safe. Road cuts may lie inside a highway right-of-way, on private property, or within an active mining claim. Loose rock, traffic, unstable slopes, and falling material make these exposures genuinely dangerous. Observe from a safe distance and confirm permission before removing anything. When examining a vein, record its width, orientation, texture, host rock type, and relationship to nearby structures. Look for repeated parallel veins, cross-cutting vein generations, broken and re-cemented rock, altered wall rock, and visible sulfide minerals. Those observations carry more weight than the color of the quartz alone. Iron staining is another indicator worth noting. Pyrite, pyrrhotite, arsenopyrite, and other iron-bearing sulfides oxidize when exposed to air and water, producing iron oxides and hydroxides that color the rock yellow, orange, red, or brown. A strongly oxidized zone developed over sulfide-rich mineralization is called a gossan, and finding one means sulfides were once present in quantity. It does not confirm gold. Gossans develop over deposits of iron, copper, lead, zinc, and other metals that may carry little or no gold at all. The intensity of the orange or red color does not measure the original sulfide content or grade. Color is affected by mineralogy, drainage, acidity, weathering, and the composition of the host rock. If a gossan turns up alongside quartz or alteration, examine the full exposed zone. Record changes in rock type, structure, vein density, and alteration across the area rather than fixating on one spot. Collect separate, properly located samples rather than grabbing only the brightest or most mineralized-looking pieces. Selecting unusually attractive material produces biased results that do not represent the structure as a whole. Historic mining districts make logical starting points because their regional geology and mineral occurrences are often documented. Old mine locations can show where mineralized structures reach the surface, but they do not prove that nearby ground is open, safe, or worth developing. Never enter an abandoned mine. Collapsed workings, unstable ground, bad air, Hidden shafts, explosives, and contaminated water have killed experienced miners who knew the risks. Before visiting a district in the United States, consult State Geological Survey maps, United States Geological Survey publications, and current land and mineral records. Federal land and mining claim records are available through the Bureau of Land Management. The right to walk across the surface is not the same as the right to remove minerals. Some historic reports are useful but require interpretation. Terminology, coordinates, analytical methods, and production figures from old documents may not translate directly into modern practice. Some reports were written for specialists. Compare old information against modern maps and avoid assuming that an abandoned mine was profitable, fully mined out, or accurately sampled. Use a compass or mapping application to record vein direction. Every sample should carry a unique identification number linked to its exact location and a written geologic description. Photographs should include a scale object. Finding quartz, iron staining, sulfides, or a visible metallic particle is the start of an investigation, not the end of it. A single piece of rock, regardless of size, cannot establish the average grade of a vein. Gold is often distributed irregularly. A rich particle can sit directly beside rock carrying almost no gold, a problem known as the nugget effect. A hand-picked specimen can therefore produce an exceptionally high assay result that tells nothing about the surrounding material. The opposite is also possible. A small sample may miss a rich particle entirely and underestimate what the vein actually holds. For exposed veins, geologists commonly collect channel or chip channel samples across the full true width of the structure at multiple locations along strike. Wall rock may be sampled separately. The goal is a consistent amount of material collected across a defined interval rather than the pieces that look most promising. Professional programs include quality control samples, accurate surveying, documented chain of custody, and an accredited laboratory. Gold has a density of roughly 19.3 grams per cubic centimeter against about 2.65 for quartz. That density difference allows liberated gold to stay with the heavy concentrate while lighter material washes out of the pan. Panning is not a complete analytical method, however. It may miss microscopic gold, very fine particles, gold enclosed inside sulfides, and gold minerals that were not fully liberated during crushing. If a pan holds a bright yellow metallic particle, inspect it under magnification. Gold is malleable and tends to flatten rather than break under pressure. Pyrite is brittle and breaks. Mica separates into thin, flexible flakes and can reflect light strongly enough to fool a quick glance. The malleability test works for visible particles, but very small grains may be impossible to test reliably in the field. A streak test helps with larger specimens. Native gold leaves a yellow streak. Pyrite commonly produces a dark greenish-black or brownish-black streak. This test is not practical for microscopic flakes and should not replace magnification, density separation, or laboratory analysis. Finding repeated free gold across multiple samples from the same structure justifies a more careful investigation. It does not establish an economic deposit. The vein may be narrow, discontinuous, or highly variable. A pan showing no visible gold does not prove the rock is barren either, because the gold may be microscopic or locked inside other minerals. Vein width also requires careful interpretation. Veins pinch and swell along their length, and ore shoots tend to occur near bends, intersections, changes in orientation, or changes in host rock. A wider section is not automatically richer. Grade, thickness, continuity, mineralogy, metallurgy, and mining costs all have to be weighed together. The reliable way to determine gold concentration is to submit representative samples to a qualified laboratory. Fire assay is the standard analytical method, often followed by gravimetric or instrumental measurement. Depending on the expected particle size and nugget effect, the laboratory may recommend a larger sample, screen fire assay, or metallic screen analysis designed specifically for coarse gold.